So now our next speaker is actually on the other side of the world and is dialing into us from Canberra in Australia. And we've got Xavier Sirault, who's a good friend of ours and has visited here a couple of times previously. Xavier is the in-charge group leader for the phenotyping center that CSIRO runs in Canberra and in several other parts of Australia. He's an agricultural engineer by training, but he did a second degree in quantitative genetics, so he's got a very interesting background, and a PhD then in plant sciences. You will see from some of the work that CSIRO have done, not only are they very good at plant biology, but also they have shown a real flair for the engineering side as well. Xavier was fully planning to be here, but ended up with an unavoidable conflict, and so we decided, as we're such a high-tech group anyway, that we would make sure that we could do this. I think we were about 17 hours difference between here and Canberra, so Xavier it's already his morning, but we're very pleased to beam him in, and the title of his talk is Practical Applications of Phenomics in Breeding Programs. So Xavier, we're going to see you on the screen in just a second.
Excellent. Thanks very much for the introduction, Maurice. I hope that you hear me well. I would like first to thank the Global Institute for Food Security and P2IRC for inviting me to address you today. Again, my apology for not being physically present with you. I had some unexpected issues with my family. And as Maurice mentioned, I'm speaking to you from the future, and so I think it's actually quite good that we're doing this through video conferencing. So without further ado, and as the title of my talk indicates, the actual context. It's not. Okay. So the actual context for this presentation is breeding and pre-breeding application, and in particular how we've started to integrate Phenomics technology and tools into our breeding programs. So we are still right now establishing the value of those tools within the breeding program, and that's done with the industry and in consultation with the industry. Just as for context, we only started 10 years ago in actually building some of the machines and the analytics to analyze the data. So bear in mind that it's going to come. We'll be able to put a figure on the value in the next few years. So I guess everyone has seen a wheat trial or trials for different crops. This is how it looks like in Australia. You've got tens of thousands of wheat plots that are being sown. I will take wheat as an example in this case, but we've got the same issues with barley or triticale, canola, cotton, sugarcane, and the like. So what we have is a range of essentially genotypes that are being put across environment, and the idea is to extract metrics from those plots. So phenotyping for us is really aiming at the quantitative measurements of traits, diverse features such as photosynthesis, for example, growth, biomass accumulation, architecture, and we're trying to basically develop tools that allows our pre-breeders or plant physiologists to be able to access that information at scale. So contrary to a genotype, a phenotype rarely has a single discrete descriptions, and most of the phenotypic characters of plants are better described as continuous function. And it's what I've tried to basically illustrate on this graph here, where you take one genotype, so in this case genotype 1, and you're looking at a phenotype, let's take it as biomass, for example, and you're looking at the evolution of this biomass across time, and how it develops during the growing season, but also across environment. That allows you to basically describe that genotype by a phenotypic surface response that you can see here. Basically, every single environment will give you a slightly different answer. And by understanding and by knowing this hypersurface response, which is essentially an illustration of this formula, phenotype is an interaction between the genotype, the environment. Obviously, you can put some management practice as well on this to change that environment. And by understanding this actual surface response, you can really develop varieties that have got commercial benefits to our farming community. Obviously, one of the advantages of using phenotyping technologies is that we're not measuring one thing at a time, but we're measuring multiple phenotypes at the same time. And so, in fact, that surface is an hypersurface response where your phenotype is described by an n-dimensional vector, which basically can be described across time and environment. And obviously, this is posing some issues in terms of statistics, and I'll come to it in a minute. So, and just to give you an idea of the scale, in Australia, each year, just for wheat, we've got over 1 million wheat plots that are being sown, and we're basically trying to provide tools that will allow us to measure those 1 million wheat plots each year. And we want to do this not only for wheat, but also for those other crops that are essential to the economy of the country. So, in terms of the aspects of Phenomics and how we can actually use Phenomics to increase the rate of genetic gain. So I'm not going to give you a course on quantitative genetics. I just want to mention that genetic gain can be, essentially can be acquired through indirect selection or direct selection. So you can actually measure the traits of interest, let's say biomass, or you can measure a surrogate of that trait to be able to select for yield, for example. So that's in an indirect selection way. So the way we're using those tools, the consequences of those equations that are here basically indicate that to influence the rate of genetic gain, there is 4 things we can do. One is to increase the accuracy at which and how we're measuring things. So increasing precision and repeatability. So this is where those machines that are being deployed in the field are used for. Obviously, this needs to be combined with a set of new statistics and also modeling. And I'll come to it because I think the modeling is the thing that's going to allow us to really integrate across scale. The other things that we can do to influence this rate of genetic gain is around population size. So population size, if you increase the number of lines, so you need to increase the throughput so that you can actually measure this at scale. You can also increase the number of environment, which basically will have for effect to increase your heritability or the actual proportion of the phenotypic variance that you observe, which is controlled by the genetics, underlying genetics of that genotype. And you can also use this Phenomics technology to increase the genetic variance. In some ways, it's more about screening germplasm diversity, all of those germplasm bank that we've got, but also trying to look for new traits that can be introgressed into our lines so that farmer can benefit from it. In Australia, for example, we work a lot on traits trying to improve transpiration efficiency or salinity issues that are quite prevalent. The other bits that can be used is obviously for a rate means that there is a time in the equations, and so it's decreasing the generation time from one generation to the next. This can be achieved not too much by Phenomics, but more by associating genomic selection tools, for example. So today I'm just going to talk to you about 3 things to keep things simple. I'm going to give you a very quick overview of what the Australian Pond Phenomics Facility is trying to achieve. Also, I've already given you a sort of some points about it. I'm going to show you how, and I will focus essentially on field applications since we're in breeding and pre-breeding for this presentation. It's applied research, so focus on applied, how we apply this in a practical context. And then one essential part of translating the tools that have been built to collect data. How do we actually grab that data and we transform that into information? And this is the role of those analytics pipeline, which are cloud-based, called Phenosmart. You can actually see Phenosmart as an app store where we've got a range of apps for the different tools that are being deployed, and that allows people to access workflows that transform your data into information, the information being traced in the context of this tool. This platform is actually available at national level through the Australian Access Federation. So anyone having an EDU at the end of their name, .edu, will basically be able to access that and access the tools that are being made available. So in terms of the Australian Plant Phenomics facility, the investment since 2007 has been over $100 million now, Australian. It's a distributed national infrastructure for high throughput as well as high resolution phenotyping. So we've got 3 nodes, 2 nodes in Canberra, one at CSIRO, which I lead, a node across the road from CSIRO at the Australian National University, specializing more on model plants and genetics or genomics to phenomics relationships. And then the plant accelerator at the University of Adelaide, which basically focuses a lot on high throughput system in glasshouse or controlled environment conditions. This is funded entirely by the government, the Commonwealth government, and as part of this, we have to provide the tools to the research community, but also to the industry to basically get innovation going. We are a complete part of the innovation ecosystem in the country. So what we're doing is a lot of research development, but also extension in agriculture. So we're going from basic research for trait discovery to basically applying the tool into breeding and breeding area. We're moving currently into improved agronomy. In the debate previously or before, the panel was discussing around how do we actually translate that to farming community. For us, it's a lot around a private-public partnership, but also with extension offices, because we don't think right now the tools we've got are going to be able to be used straight away by a farmer without someone interpreting the different layer. And then moving to precision agriculture, so that essentially the information collected can actually be passed on to growers and farmers through those extension offices. And obviously, the result of that is a consumer that has got access to better product, a country that has got a better economy, and the like. So what do we offer is essentially, since the beginning, since we've started, we've actually built from scratch a range of platforms, and we're trying to make them translational. So going from basically the control environment to the complete open field or vice versa. We have 2 complementary approach, a control environment, which allows us to apportion confounding effects when you're doing an experiment, and provide a sort of mechanistic understanding on how the genes are controlling the phenotype, but also a field approach where we are trying to operationalize what we've learned for high throughput phenotyping in pre-breeding trials. So this is done at different levels, single plant level, mini canopies, again in control environment, and that is being translated through a range of platforms, which I'm going to basically discuss today. The Phenotyping platform, an IOU platform, and a sensor network platform, and how this is applied in a breeding context. All of those platforms fed directly into Phenosmart Analytics, and all of those platforms are using a range of sensor technologies that are similar across all of them, from fluorescence to LiDAR, RGB, hyperspectral, and the like. So our philosophy really is going lightweight and portable. So what I want to say, I'm not putting this as a way of saying this is bad. I'm just saying that what we want is really having platforms that are that we can distribute to the different breeding programs across the country. And if you go something monolithic like what you've got in Rotham State or in Maricopa, you are quite limited to what can be done. So we've actually built a range of platforms. So this is actually a commercial system now that has been licensed to a company for distribution. Comprises a range of sensors, and the platform is propelled by electric motors and allows you to digitize the crop as you go along. The throughput is around 1,000 plots per hour and is adaptable, as you can see, can adapt to different crops. This is in onion breeding trials and in cauliflower breeding trials here. So the platform can adapt in width, in height, to the crop of interest. We've actually used this platform for a range of commodities, barley, canola, sorghum, cotton, some vegetables, and we're currently moving into fruit like strawberries and raspberries. So the main technology that we're using at the moment on this platform is LiDAR, so light detection and ranging. It allows you to basically digitize in 3D the wheat plots, in this case, an example here of hydrogenic lines varying for height. And it allows you to essentially emit a laser. When the laser hits an object, it is basically bounced back to the sensor, and the sensor gives you a position in space for that little point that has been reflected. From that, we essentially use PhenoSmart to extract validated traits such as canopy height, fractional ground cover. We've got a range of biomass indices, greenness vertical distribution, for example, if you want to look at senescence profile. And this allows you over time to look at how this trait is evolving. So we're developing as well analytics or new statistics to automatically fit those growth curve and derive from those growth curve a range of other traits like when the maximum growth rate occurred, what are the, a range of traits essentially. So how does this work? So as I say, we're collecting the information. The data is being pushed into PhenoSmart. So this is a cloud platform. It's allowing you to aggregate the data and to visualize the data. So this is just one example for a LiDAR file. So this is a wheat plot seen from the top. It's a LiDAR signal. So it's a 3D point cloud that is displayed in this web browser. And it allows you to basically determine which area needs to be analyzed. This can be done automatically or can be done, can be adjusted manually after an initial cutting by the computer itself. It allows you to visualize where you are. So in this case, we were into a polytunnel, which is part of the infrastructure here, and then allows you as well to look at the metrics at the plot level or at the single or dual row level. This is something that has been requested by our pre-breeders, particularly at the early stage of the selection process, where they want to do allelic enrichment in early generation, so they don't have to test millions and millions of things later on. All data are delivered into various formats. The most common is a CSV format, and then the scientist can actually use this in different ways and visualize this in different ways. So an example of that is canopy height. In this case, I've got, again, a LiDAR file here. So it's a 3D point cloud. I've got a transect across 3 isogenic wheat lines, which differ with the height genes they've got. And as you can see from that transect, this is basically the height, the representation on the of the plots across that transect. So you can see that there are differences in height between those plots. And when you're comparing your manual measurements versus your measurement done automatically, you can see that you've got a very good relationship here, almost a R-square of not a 1. And this is the 1, 1 line. So we are very confident that what we're measuring with this system is actually relevant. As I say, this allows you to do 1,000 wheat plots per hour, and we're measuring other things as well, as I'm coming to it now. So one of the other things which would be very hard to measure by hand is biomass distribution and stay green profile. So in this case, again, in this panel, I've got 2 lines. They've been selected, the isogenic lines, and they've been selected for radiation use efficiency. So in line A, you can see that basically, so what we're seeing here is the plot width. So this is a LiDAR point cloud. This is the plot width, so it's around 1.80 m in width. This is the height of the plot, and all of those points is the density from the LiDAR information. So as you move along, a plot is 10 meters long. We've aggregated those 10 meters of length into the plan height versus plot width. From that, we can actually aggregate the data into a density distribution, which basically tells you where the leaves are in this canopy. As you can see between line A and line B, again, high radiation use efficiency for line A, low radiation use efficiency for line B. You can see there is a difference in the actual profile where the low radiation use efficiency line has got much more biomass in the middle, which in fact prevents a lot of the light going into the lower layer. This has for consequence an increased senescence at the bottom of this plot, and this is represented by the greenness that we've overlaid on that distribution. So red being a lot of senescence, green being new leaves that are quite fully functional to do photosynthesis. So this is allowing you to do this kind of measurements at scale, essentially. So last year, just to give you an idea, we've screened over 300,000 wheat plots like this with the Phenomobile. So we've got 5 of them across Australia, and there is actually a new Phenomobile going out, 2 breeding program, to the Grain Research and Development Corporation to basically measure those wheat lines in that way. Finally, that would be the last example for the Phenomobile light application again. We've developed a range of biomass indices that allows us to look over time. So this is the biomass. So the color represents time, so time periods. So in this case, we had 1, 2, 3, 4, 5 different measurements of biomass that were done both with the Phenomobile, but also by destructive sampling, just to be able to show you the relationship. And as you can see, we can actually distinguish variation across line in the way they accumulate biomass. But what I really want to point out is the different methods and the effect it has on the heritability. So how confident we are that if we select a variety today, that basically the phenotype will appear in the next generation. And as you can see, a manual measurements of biomass give you an heritability of 72%. So this is actually quite high as an heritability. Breeding program typically think that things that are above 0.6 or 60% heritability are great to be used in their breeding program. But as you can see, the LiDAR information is providing an heritability of almost 90%. So manual, this has got a lot of labor involved into it. This is basically 1,000 wheat plot an hour and can be done by one single person. So essentially what we're demonstrating here with this table is that the LiDAR information is actually providing you something that is highly repeatable and that you can be even more confident in your selection. So as a roadmap for traits, currently we've got those traits being output of PhenoSmart. In the future, and that's what we're working on at the moment, we're working on things like functional staggering by combining canopy temperature and LiDAR information, spike counts, looking at photosynthetic pigments for improvement into photosynthesis. And in the future, and that's already we have already started to work on that, things around water content, leaf angle distribution, and a sort of harvest index, which is non-destructive by nature. The thing that is of interest to us now is to link into modeling platform like AppSim. So this is some work that is done by Scott Chapman and Bang Yu Zhang in CSIRO in Brisbane. And essentially what we've done is taking some UAV images of the same plots and calibrating with those UAV images the model that runs into AppSim for wheat. So what we've done is looking at the calibration of ground cover in that model. So we've got, as is represented in that quadrant, and we've also calibrated the phenological stage of that crop. And then we've actually computed by the model, so by just providing this and in real time, almost updating those calibration, we can basically derive for at any period of the growing season your evolution of leaf area index for the crop, but also the evolution of total biomass. What I'd like to show you here is the line, the curve that is here is the model, and the actual triangles or round circle here are measurements, descriptive measurements that have been done on this crop. One of the things we didn't tell the model is the difference between the blue line and the red line. The red line is actually a nitrogen treatment, so the model didn't know we put a nitrogen treatment, but the model was able to say, well, based on the calibration you've given me, there is a difference between those two sets of data, and essentially that gave us the confidence that the model was pretty good at replicating what has happened in that current season. What it allows you to do this is now extrapolation. So you can actually use things like measurements of the water usage pattern during the growing season for all of those wheat plots. So thousands and thousands of wheat plots. So you can actually look at how they've been using water. You wouldn't be able to do this using direct measurement methods. AppSim is also being rolled out as a tool to the industry so that they can do prediction about when farmers should actually put nitrogen on and so on. So we hope that basically combining phenotyping technologies and output from this phenotyping technology with the model, we can in fact improve the advice that are provided to farmers through AppSim-derived products, which are used by extensions officer in particular. So the next technologies, and we've done over 500,000 wheat plots this year and last year as well, is this platform, which is an helicopter and which has an helipod fitted to it with thermal imaging sensing, multispectral sensing, RGB sensing. This is the size of a trial. That's only one trial out of many. And we can collect over 4 minutes, 10 hectares of information. This allows us to do extraction of metrics like plant height, overlaying multispectral information, or looking at thermal imagery, which gives us information about how the crop is transpiring water. So again, for this wide thermal infrared sensing as a technology, we can use this for irrigation scheduling, and we've actually demonstrated this quite nicely in orchards. I haven't got any example here, but we've done that work. For phenotyping for salinity and transpiration efficiency, or for screening mutants. So the idea of using thermal is that the leaf temperature is a function of the stomatal opening. So the little pores on the leaves that allows the water to escape. And as the leaf temperature, as the stomatal opening is increasing, the leaf temperature decreases. It's the exact analogy to when you come out of the swimming pool, you've got water on your skin. As the water evaporates, you're feeling a cooling effect. So this gives you an example here from one of our publications about a non-transparent surface being very hot, red, as you can see here on the scale, and a surface here on the tree that is quite cool because of the open stomata. So how do we apply this? Again, PhenoSmart allows us to basically collect that data. There is around 10,000 wheat plot in this image. You can visualize that data within your web browser. It allows you to basically extract the information from those 3D reconstruction automatically, but also overlay information on top of them. So how it's been used, one more thing. So we are completely agnostic to the platform. So if you're using a UAV, a lot of people are now equipping themselves with UAV platforms. We basically grab the data and we're doing the same process through PhenoSmart. This has been done in particular on sugarcane, which is a crop that is 6 meters tall, and it's very hard to be able to get in on the ground. So UAV platform are the tool of predilection for those companies, like Sugar Research Australia, for example. From these, we also do the same thing: crop cover estimation, canopy temperature, head counting in sorghum, for example, here, and automatic estimates of 3D lodging if you've got an issue with wind and lodging in your crop. So what we do as an application, each image is analyzed automatically. We essentially extract for each plot the temperature information with its distribution. This is overlaid automatically on your experimental layout. And from that here, in this case, you can see there is two things in that trial. So this is a recombinant inbred line population that has been selected or segregating for transpiration efficiency. One side of the plot here in blue is irrigated. The second side of that trial is actually rain-fed. The color represents the temperature, and as you can see, obviously, the rain-fed is much hotter than the overall treatment where it's irrigated. When we use this information on the actual map that is available for this population, you can actually map the QTL for transpiration efficiency. So what we've got here are 4 time points during the day, 10 o'clock in the morning, at noon, 2 o'clock, and 4 p.m. And then we've actually mapped it. So you can see there is congruency different in the same area, I guess, on the genetic map. And what I've actually displayed there as an arrow are QTL that were identified by other methods over the last 20 years, particularly work from Rebetsky. And as you can see, those arrows, so QTL that were identified previously, are congruent with the new area identified by using those new methods. What we've done as well is improving the irritability, because we can actually measure this within minutes, while the arrows here were measured over hours. And we go from an irritability of 10%, meaning that most of the measurement you're doing is noise, to over 70% today. So we can also be confident about the actual value of the technology and the information we're getting out of the trial. This is actually being deployed now into big multinational companies' field trials. I'm not going to give you names, but essentially it's being used extensively in the country. Finally, sensor network. So these are a range of sensor network that use the 3G or 4G network to relay information on a second-by-second basis. It allows us to do continuous measurement at canopy level or of what the water is doing into the soil, and we are associating this with environmental measurement to be able to interpret the phenotype of the crop over time. We've got around thousands of those units deployed across the country, both on wheat trial for canopy, for transpiration efficiency measurement, but also now it's been moved in cotton for irrigation scheduling. What do we do with this? So the data collect, we've got over 60 billion data points now over the last 5 years that have been accumulated. What it allows you to do is aggregating the data. So in this graph here, or this representation, I've got a range of genotypes, the wheat genotypes on this axis here, and the time of the day from midnight to midnight. So what we're doing is we're measuring the color represent the deviation from the hourly mean for the whole trial, of canopy temperature for the whole trial. So obviously, when it's nighttime, there are no differences at all between all the different lines. Same thing when the sun sets, there is no differences at all there. However, during the day, as you can see, and there is, in fact, so this represents the day, so from midnight to midnight, as I say. So you can actually start picking up differences between lines. For example, this one is a line which basically gets much hotter, so it means that cannot access water, versus this line, which is much cooler. And so what we're trying to do is identifying the genes that explain those differences. And the other thing I wanted to mention is your irritability during the day is increasing. As you can see, the signal strength around midday is much higher than at any other time. So you can actually use this tool to pick up as well at what time of the day you should do your measurement, so that you can increase your irritability and you can be confident that the genes that you would have selected in that line will be there in the next generation of selection. So to finalize, what we're trying to do is improving by 20 to 50% the research efficiency in pre-breeding program by the use of those enhanced tools and analytics. So the old way, 2 examples here that I've drawn and that I've explained today. The old way with manual cuts, where we're doing plot biomass measurement, took around 5 people and 80 hours of work to do 1,000 wheat plots. We now do this within 1 person in 2 hours. So this means not only collecting the data, but also the analysis of it. The other thing is around canopy temperature. The whole way was having a team of a technical officer going in the field with infrared gun, measuring something that gives you an heritability of around 10%, so essentially a lot of noise, taking you hours and hours, versus the Phenotyping platform, which is basically the association between this ELIPod and its content and the analytics, will take you basically an heritability now going over 70%, and you can do hectares of it at once. And those two technologies right now are a major investment in by the industry. So industry has come to us, is using that technology within their business processes to improve their efficiencies in the selection process. So I'd like to finish by acknowledging my team. We are 22 people, not all of them are here today. And all of this work is their hard work. And plus obviously colleagues across the country at CSIRO, University of Queensland, INU, and the like. So thank you very much for your attention. So thank you.